quick edits before I can get it out to everybody by email. If you're interested, of course, in learning more or would like to see some additional videos or information, you can reply to that email and I can send you whatever it is you're looking for. So for today, throughout the presentation, feel free to ask questions. You can submit them using your interface on the right-hand side. As you submit questions, I'll try to answer them or propose them to Don Jacerta, our presenter today, throughout the presentation. If we're not able to get to your questions, we have some time set aside at the end, which I'll go over in the agenda in just a moment, that we'll be able to address all questions we didn't get to during the presentation. Upcoming, so later this month, we have another webinar, which will be on our plant solution for combining inspection reporting, real-time monitoring, satellite stations, and data input in a plant environment in order to give yourself real-time monitoring, analytics, and metrics about your manufacturing processes. The exact details will be going out in DCS's newsletter, which should be heading out mid-next week. If you're not receiving our newsletter, of course, I recommend you join our newsletter by going to our website at www.3dcs.com, going to the Contact Us tab, and clicking on Join DCS Newsletter. There you can enter your email address, and you can join DCS's beta tester, user newsletters, or just our overall newsletter, which we send out only once a month, so it won't be spamming or filling your inbox. Today's agenda. So we're going to begin with a brief introduction about DCS. We'd like to talk about the cost of quality, then predictive versus reactive, connecting processes, followed by an example case, and a couple minutes at the end for Q&A. So we're looking at about 40 to 45 minutes for a presentation with a couple minutes at the end for the question and answer, and we're looking to wrap up within 60 minutes so you can get back to your day. So my name is Ben Reese. I'm your moderator today. I'm part of DCS's marketing team. Your presenter today is Don Jacerta, DCS's Vice President of Sales. Now, Don brings more than 30 years of engineering process improvement experience to his role as Vice President of Sales at Dimensional Control Systems. He leads the sales and process transformation teams here. He started his work life early. Growing up on a dairy farm in Wisconsin, has been involved in a variety of manufacturing and engineering process improvement roles with companies in the automotive, aerospace, medical device, and machinery industries. He began his career as a manufacturing engineer in the NC programming group at Square D Company in Milwaukee back in 1977. Over the years, he's lent his process improvement expertise to a variety of leading-edge projects ranging from artificial heart valves to composite aircraft, green energy, and most recently, electric vehicles. At this time, I'll be passing the presentation over to Don Jacerta. Don, if you want to say hello.
Good morning, everybody. Okay, are we ready to go?
It looks like it.
Okay.
I'm just going to put out a question real quick to make sure everyone can hear us clearly before Don gets started. If you go ahead and raise your hand if you can hear us all right. You can do that by clicking the raise hand button on your interface. All right, excellent. Thank you for that. I appreciate it. Good. Looks like we're being heard loud and clear. All right, Don.
Thanks, Ben. So I would like to just start by introducing DCS to those of you who are not familiar with who we are. We are a quality assurance solution provider serving a variety of manufacturing industries. Many people know us well in the aerospace and automotive industries, but we have a strong presence in the electronics packaging, heavy machinery, consumer goods, and medical device industries as well. And as some of you may know, we are both a software supplier through a set of tools that are part of supporting a quality assurance process for manufacturing, and we have a service business that is about applying those tools and about addressing the needs of quality in manufacturing. And I'll talk some more about that as we go along. So as we think about the topic of today, we always want to frame where we're going with what we're doing with our customers around the topic of cost of quality. And this is a chart that has made its way around, it's produced by the analyst community, but it is a very simple depiction, and that is that the earlier in the product life cycle a defect can be identified and addressed, the less costly that defect is from the standpoint of the producer. If it's addressed during the design phase, the cost is very low. As you move into the production area, the cost, once tooling is already been produced and design freezes have occurred, that cost goes up significantly. And of course, when you think about the cost of warranty and or liability issues, once the product has reached the customer, that cost becomes significantly higher. So as we look at these elements and think about how to address them, we break this up into kind of four distinct areas that have to do with the costs I spoke of. Thinking about at the very end, where we're talking about an external failure that have to do with returns or warranty claims, and then thinking about the early stages of prevention, where there is simulation being applied during the engineering process, and a more detailed approach to design is taken to prevent these problems. You can see how these elements directly affect the cost within the context of the product life cycle. So the overall strategy that DCS advocates from the standpoint of driving quality is something called dimensional engineering. And dimensional engineering, while I won't get into great detail on the 8 steps of it today, some of the major elements of it are, first and foremost, that it is cross-functional. And when I say cross-functional, what I'm saying is it works across both the engineering, that is the product engineering, and the manufacturing organization. So as organizations have different structures, there is typically a group of people who are responsible for the design of the product and the definition of its specifications. Those specifications, when it comes to dimensional characteristics, most often being defined as in terms of GD&T. And then there are engineers who are responsible for defining the manufacturing processes of how those products are going to go together. What are the fabrication processes? What are the assembly processes? What are all the elements that are going to be necessary in order to make that fit together? And so when we talk about this, the cross-functional element is vital, number one, and the second thing that is vital is that it begins very early in the product life cycle. So when I talk about something like program directives, that means the understanding at the very beginning of the initiation of the program, what is the intent of the product? And at that stage is the time to begin thinking about what are the dimensional implications of this from both a producibility standpoint, a cost standpoint. It can have to do with the types of processes, the types of materials, who might be the sources of components that are used in the product. And then there's a series of activities that go right on through down to the end state of manufacturing and doing problem solving or root cause analysis, and having all of those elements be interrelated. The objective of all of this activity in dimensional engineering is all about controlling variation. Variation is ultimately the problem and challenge that everyone as a manufacturer deals with in terms of getting the product to build correctly and function correctly for the customer based on the intent. And so when we think about this from this perspective of the dimensional engineering process, we talk about coming at this from two directions. One is a predictive approach, which is based on engineering simulation, and the other one is a responsive approach, which is based on monitoring and problem solving based on measurement during the production process. For the sake of today's discussion and topic, we're going to focus on the latter part of the dimensional engineering processes, which are those that have to do with simulating variation, and then from that, from the simulation results, being able to have a consistent approach to measurement that is used during production, being able to use the information that's gathered during that measurement process to be able to track and understand quality performance, and then being able to use that information from a root causing perspective and creating a feedback loop that is then being able to support solving the kinds of problems that we talked about, such as stretch, flex, and springback, that are effects of variation in manufacturing. So one of the key elements that we'll talk about today is the notion of developing process capability. The idea is that there is an efficiency to be gained by understanding process capability and being able to apply it both in a predictive sense as well as a responsive sense to supporting quality. The notion of being able to automate processes that have historically or typically are thought of as manual in the definition of process capability. Being able to use 3D CAD as the master, or as is referred to in many industries. Aerospace in particular these days talks about model-based definition, or MBD. The whole idea again around MBD is 3D CAD as the master source of information, creating feedback loops between engineering and manufacturing, using data for providing a continuous improvement environment that enables ongoing development and improvement of products and processes to be realized in a very live and or real-time sense. And of course, as you saw in the earlier slide, this notion of being able to control variation by connecting the predictive and reactive or responsive elements of, in this case, process capability. So if we look at this, first of all, coming from the plant perspective and talk about this in terms of quality management, the aspect that I'll talk about from an example standpoint very quickly is controlling quality from a standards basis. Different organizations have different elements or statistical aspects that they are concerned about. In the auto industry, for example, CP and CPK are very critical, having to do with capability and having to do with consistency of production. In the aerospace industry, these are becoming more and more relevant, as well as statistical methods are becoming more accepted, are becoming more applied, as we see build rates of aircraft continuing to climb to bigger and bigger levels. being able to perform these kinds and manufacture these kinds of statistical parameters. As I've said before to many people, not relying on things like rework as a standard part of a manufacturing process, or fabricate to fit as a standard element, that standard components on a broader and broader basis have to be able to fit to the overall assembly process. These elements become more and more critical. The way we're approaching this is to connect all these processes together. Dimensional engineering, as we talked about, is a continuous process, and a process that cuts across the engineering and manufacturing domains, and requires a collaboration between engineering and manufacturing, product engineering and production engineering. And when we think about this, and from a variation control perspective, we think about it in a simple context of starting with prediction, from the prediction being able to plan the work that's going to be executed based on the outcomes of those predictions, using that plan to drive a process, and then from that process being able to identify or find where issues exist, and then once those issues are identified, being able to use that data effectively to resolve those problems and provide a correlation loop to the original prediction to drive that continuous improvement element that was spoken of just a moment ago. If we look at these in a real sense, then we start to be able to look at the processes around predict, plan, find, and resolve that are relevant. And I always think about this slide and talk about this slide not for what are in the graphics or in the big boxes, but it's the key elements that are part of the arrows, the steps in between that are the key elements of driving this closed loop and continuous improvement process. So for today, we're going to take a look at a case study that we'll use for our example discussion on addressing effects of stretch, flex, and springback. We're going to use a tail section assembly that is part of an aircraft. So if we look at the first element of this, is understanding the effects of stretch or flex or springback based on doing simulation in a 3D CAD environment. In this case, we're using a CATIA-based application, 3DCS, for executing variation analysis. And in this case, when we talk about things like the effects of stretch, this is a real-world example. If you go out, you would find a number of cases on aircraft skin assembly and the variation occurring in aircraft skin assembly due to the clamping and drilling and riveting process, and the effects that are induced into the skin as part of that process, and from a deformation perspective, and then what happens when this tool is unclamped, and what happens relative to all of this force or stress that's induced into the assembly, and how to start to consider that and compensate for it. That's an element of what we're talking about in the use of variation analysis. In this case, variation analysis that takes into account finite element data for being able to execute what we'll term a compliant analysis or a compliant model, which is considering the effects of deformation during the analysis. So for those that are maybe not familiar with this process, the process takes into account the individual parts that make up the assembly. Those parts are identified, and the assembly process or indexing process is then defined and executed within this simulation environment. Once the assembly process is defined, then the definition of a measurement approach and application of the tolerances, whether they be tolerances defined in a drawing, a GD&T sheet, or a semantic tolerance defined in the 3D CAD model-based environment in the form of in this case, CATIA, FT&A. Those are applied, and a Monte Carlo analysis is executed in order to be able to understand what the effects are. Again, thinking about the use of the finite element data to now take into account the impact of deformation that is caused through some sort of an effect that is going to cause these, in this case, the external skin of this aircraft to stretch or flex. In the case of an automotive tool, it may have to do with what occurs after a stamping or forming process, where there would be some level of springback that would occur as the part is removed from a stamping tool or some sort of forming die. So the outcome of that analysis, of that simulation and analysis, is going to be to start to identify what are those contributors that are going to affect variation. And based on the analysis that's executed using the finite element data, be able to have an understanding of how that flex is occurring, where it is occurring, and what's happening after the release of those parts from the tool. One of the downstream outcomes that we talked earlier about was from an analysis being able to create a measurement plan for the plant to execute manufacturing. Once the measurements are defined through the analysis process, these measurements can then be output in the form of a measurement plan, or can be output in a data set that can be directly passed to a metrology software or a measurement software that may be used to drive some sort of a measuring machine, say a coordinate measuring machine, or a laser tracker, or some sort of a measuring device. Again, this notion of coordinating the measurement strategy between analysis and plant is a key aspect of driving an effective dimensional engineering process. So once the measurement plan has been defined and production is underway, whether it's at a single piece prototype level or at some sort of a production level, the idea of being able to manufacture and then measure to the intended plan begins the first step in the ability to, of course, validate a part, but then be able to use the information from that validation, that measurement process, and be able to begin to develop a set of data that can be used to define process or understand process capability. So in that approach, the idea is to be able to take all those outputs from, in this case, the measurement of a tool that is used as part of the forming process for the skin, and be able to aggregate that information and be able to have it be understood and accessible and usable, not only as part of the validation and assurance of manufacture to specification, but also be able to use it to, as I mentioned, build a data set that can be used to define process capability. If you're building across multiple locations, plants in different areas of the country or the world, or potentially supplier information, being able to have visibility of this is also becomes very relevant in being able to bring data together to understand capability, not only as part of your own manufacturing process and part of your own assembly process, but maybe that of a supplier or of your customer. And the idea of being able to understand the quality performance as quickly as possible, as soon after the measurement of those parts and tools occurs, is another key aspect of being able to use the analysis and the data in process capability to understand these elements. So if you think about a tooling supplier, for example, who may be measuring the tool or measuring prototype parts coming off of that tool, and being able to have access to that data to be able to start to build up a data set that lets you understand the real world elements and realities of what's occurring in things like springback out of a die, what's occurring with things like flex of a skin coming off of a tool, or a stretch condition that might be coming off of a tool. This data becomes something that you can apply not just for the validation or buy-off of parts, but for the longer-term implications of process improvement, and be able to predictively understand where your issues are going to occur, rather than have to deal with finding these problems during the assembly process. Examples of the outputs of this aggregation and reporting or quality tracking that I was speaking about, you know, the notion of being able to report and track data and have quick visibility based on the automated roll-up of this information is one of the key elements of this. Another one is then being able to take that information and use it in a problem-solving sense. So as you look at, for example, where there are variations occurring on individual parts that are being fabricated, to be able to consider these in an assembly context long before you begin the assembly, gives you a sense of what issues are going to occur, in this case, from a step and gap perspective, in putting these skins together on the aircraft structure, and being able to understand if there's going to be a requirement for shimming, or if there's going to be a requirement for some modification before commencing that assembly, and consequently reducing the amount of effort and time that mechanics or assemblers are going to take to be able to put these types of things together. A third case is not just understanding and not just problem solving, but now being able to start to build an example or a base of process capability based on your machine's capabilities. In this case, we're looking at a simple example of 3 holes drilled on a bulkhead section, and we're looking at the run chart of this data being a aggregate of a single machine and its capability, and we've looked at this. We've got situations where not only are single machines being looked at, but even single elements of machines. Maybe it's how a locating scheme is working on a particular tool, or it's looking at a particular type of drill or a particular type of tool holder, and looking at the performance of those individual tools as they relate to that machine to start to understand how these capabilities can apply to the performance of a given type of manufacturing operation. So this can you can start to think about these things and understand process capability, at the level of machine-to-machine capability. So, particular types of jobs might be better suited to different types of machines in a machining environment, or if you're talking about assembly environment, you're talking about station-to-station capabilities and what types of operations should be best suited to certain assembly stations, or it may be looking at capability and saying there's adjustments that need to be made at given stations in order to make a station perform at a level that is more consistent with another assembly station. Looking at this on a line-to-line basis across an organization, and understanding what capabilities may exist on lines that are building the same or similar products, and then even looking at it on a plant-to-plant basis and being able to look at what lessons learned can be taken from a given plant that is building a same or similar product and be able to apply those to another plant, being able to understand all of this based on data. These are just a few examples that represent how this process capability information can be used. We're going to talk about this process capability and its application from the standpoint of correlation. How can we take this information, this rich set of data in an as-measured environment, and being able to apply as-produced results to as-designed intent. And when I say as-designed intent, I'm speaking not only of nominal CAD, but I'm talking about the GD&T or tolerances and specifications that have to do with the control or limitations of variation that are acceptable as part of the part of the manufacturing process that become relevant to how things are manufactured and ultimately how they do or do not fit together. So this correlation step becomes a critical element of this topic. So the idea of taking the data that's collected during a manufacturing process and being able to use that data to now execute an analysis using the same analysis model that was originally used from a simulation perspective, and rerunning that analysis with the as-built data now provides this ability to have iterations on where your issues are occurring, where are things occurring in production that didn't present themselves or didn't present themselves as significantly during the simulation process as they are showing up during the manufacturing process. All of a sudden, now you've got a new level of detail that can be realized based on information that is being input. And when we combine this input of data with this idea of being able to consider what our predictions were on elements like flex or springback or stretch that occurred on parts that have a high degree of deformability, it now provides a new level of detail in which these analyses can be executed. So the outcomes from this can be simply that there is a better understanding of what the effects of a particular deformation characteristic are, and can now account for those in terms of changes to a manufacturing or assembly process. Now that based on the measurements that have been executed, it can be understood where the deviation from nominal is occurring that may not have been as readily understood, or may have been acknowledged but not quantified because there was not measurements that were identifying what the specific detail of these variation are. So now things like process change can start to be considered. GD&T specs can now be updated or modified in order to start to think about how to account for these effects of deformation, and even cases where part designs can be changed to account for these effects of deformation in the design of the product itself that are induced because of the manufacturing processes and the effect that they have on the design. All of these characteristics can start to be considered and updates made in order to have a more consistent level of reproducibility in the product and process that is ultimately being produced and delivered to the customer. So the conclusions, when we think about this idea of using data to drive process change and the effect of elements like springback, flex, and stretch, and combining process capability with the notion of deformable or compliant parts analysis, the idea is to start to create a capability that determines a level of standard that is not only driven by consistency in the part design, but consistency in the process, and consistency in the process that takes into account those things that are occurring in manufacturing that may not be apparent to design engineers, but are real world issues and repeatable issues. I think that's one of the key aspects of this, that repeatable characteristic that is being able to be identified through process capability data and be able to apply back to considerations in the product design, so that you can manage these process limitations and be able to start to get a better understanding of where they exist, what the limitations are, and what you can do to account for those limitations earlier in the development phases, using the feedback loop that we've talked about repeatedly here. Thanks, Ben. I'll turn it back to you.
Thank you, Don. I appreciate your time this morning. Thank you, everyone, for joining us. We have a couple minutes here at the end for some questions and answers. So I'd like to open the floor if you guys want to send in your questions using the interface on the right-hand side. We have about 5-10 more minutes to address any of those that might come up. I had a few during the event. One came up while we were looking at measurement plans and looking at measurement plans. One of our customers would like to know how difficult it is to generate the measurement plans. Looking at, that they want to use with their, it said CMM machines, but I'm assuming, multiple inspection devices.
So, as far as generation of measurement plan, the biggest challenge, authoring the measurement plan is not a difficult thing in and of itself. As a solution provider, we will advocate that you would use our tools to create the measurement plan. QDM analyst representing a great tool for creating a measurement plan, but that's not to say that it isn't possible to create a measurement plan with any kind of with many different tools. The biggest element, I would say, is not about the plan itself. It's about the data. It's about the coordination of data and the coordination of data between what's going to get measured, and in the case of those of you that do simulation, what is being simulated. As I tell customers all the time, we're not here to tell you how to execute your dimensional engineering process. If you have an approach that is based on creating a measurement strategy first, that's fine. Just assure or just take the approach that the measurement strategy that's defined for production measurement or physical parts measurement is the same measurement strategy that's used for simulation, so that the analysis results that you're getting from a simulation outcome uses the same measurements that you're being used for production.
Thank you, Don. Appreciate that. So that kind of answers the next question. If we already have these processes in place, we're already utilizing dimensional engineering, how does this solution provide additional value?
Again, the thing that we find with customers, even our customers all the time, is that they have implemented tools to support specific tasks. For example, 3DCS to execute variation analysis as part of the engineering or upfront task using simulation. They've implemented QDM, for example, as a means of monitoring production quality and doing fast problem solving in production. Even cases where measurement plans are being authored with QDM, but these tools are not necessarily working in concert. And the process aspect in putting a process in place that enables everyone to be working with the same information and working to the same task is the key aspect that I think I would talk about ways to get additional value out of the overall process.
Okay. So it's more about connecting and creating a process flow between disconnected areas and disconnected tools and processes.
A process flow or even a process strategy.
So we saw a number of analyses mentioned, and you talked about about the compliant model. Sorry, I just have one or two questions coming in. I'm just trying to address here on the side. So you talked about the analyses that came in and using the results from it. In these particular analyses, could you talk a little bit of, just in brief, a little bit more about what those analyses compose of? So, like, for example, the compliant model or the variation analysis itself, the simulation at the beginning. If you could just expand a little bit on that.
I didn't understand the question.
Sure. So you mentioned a compliant model, and we talked about simulation in V5.
Yep.
Now within V5, though, the particular outputs that we're showing don't just come out of V5. Could you talk in brief just about what kind of variation analysis, say with like 3DCS, or what kind of goes into that simulation aspect of it?
I've asked Gary Bell is here also, one of our engineers that I've asked to step in, and I want to ask Gary if he wouldn't mind answering that question.
I would if I still understood the question.
Just a little bit more about what goes into the simulation part of the predictive analysis.
So 3DCS tolerance analysis is the base package is a rigid body analysis, and it picks up the geometric effects of your location method and your component part tolerances. You can extend that with an additional module called compliant model, and compliant modeling implements the FEA mesh and stiffness file from your FEA tool, which now lets us step away from what we refer to as rigid body analysis, and we can over-constrain the part, twist the part, clamp the part, and get a better representation of how this part will react in the manufacturing environment. And that also gives us the ability to apply gravity to it, thermal to it. So the compliant modeler is just the next step of accuracy on three-dimensional tolerance analysis, going from what we refer to as rigid body analysis to compliant analysis.
Thanks, Gary. And that provides that ability to understand the effect, the variation effect on the topics of things like Springback or flex or stretch that are occurring because of clamping, indexing and clamping, or some element of the process.
All right, thank you guys. I appreciate that. One last question it's fairly quick. I just want to address real fast. So I know you mentioned this in brief as you were going through, and we were focusing today on process capability. Now, if there are other metrics that are used by the company to monitor performance, something other than process capability, such as PP or PPK, a different metric. Does it matter which metric is being used when it comes to implementing these processes?
Everybody's got, different quality metrics that they are concerned about. Some are more standard or generic topics like capability, CP or CPK, or production capability. Others may be more specific to a given company, where they have certain characteristics that they've deemed relevant to their processes and to the outcomes of those processes. It really comes down to what people are concerned about. In a general sense, though, in a manufacturing environment, CP and CPK, particularly at a production level, are things that are generally thought of as being critical to understanding the capability to produce a product consistently.
Do you have an input there, Gary?
Yeah, I think maybe the question is, it can be any form of data that's used to track the quality. If they're making a shampoo and they're measuring the viscosity. Yeah. If they're collecting that information, that's data, and then we would track that data. Now, of course, that's a variation that's not a dimensional variation. But, you know, QDM is collecting data. If it's a dimensional variation, we don't care what kind, we can put that back into the tolerance analysis.
All right. I appreciate it very much. It looks like most of our questions that I haven't addressed individually. I'm going to go ahead and wrap up today's session. We're about 52 minutes after the hour, so we're right on time. I want to thank Don Gisterta and Gary Bell, one of our senior variation analysts, for joining us this morning. You'll be look to your inbox in the next 24 hours to receive the recording. In addition to the recording, I'm going to put in a couple of links to additional information, 1 or 2 articles and a video that'll help support some of the points made this morning. With only about 40-45 minutes to discuss the topic, we can't include everything. So I'm going to add some of that support material in when I send the follow-up email. If you have any questions at all, you can feel free to email us after the event. I believe our email address, the sales email address, is there. That'll go to me and Don, both of us. So feel free to send in your questions or to give us a call. We're more than happy to discuss any kind of trouble you might be having, training, or if you have just additional questions and interest. So once again, I want to thank everyone for joining us this morning, for taking the time to stay late at the office or come in and log on first thing in the morning for those of you joining us on the West Coast and Texas. Once again, that email will be going out tomorrow afternoon. And please let us know if you have any questions. And thank you for joining us.